Assigning currents. When we assign the currents, we usually have I going from positive to negative across the definition of our resistor. And when we do that, we get V equals IR. But sometimes we will end up assigning a current going, instead of from positive to negative, from negative to positive. And in that case, we define it as V equals minus IR. And in this figure down here, even though the current looks like it's going from left to right, and it is, notice the voltage definition is opposite. It's still going negative to positive, and you get V equals minus IR. And here, this is going from right to left, but the voltage definition is positive to negative, so V equals IR. And the interesting thing is, if I substitute these resistances for impedance or a DC biased diode or transistor, the way we assign these currents and V equals IR is still the same. It still works. We just start off with resistors because they're easier to understand. Let's have a quick review of Kirchhoff's current law, where the sum of the currents entering and leaving a node have to equal 0. So if I have I1 entering the node and I have defined I2 as leaving and I3 as leaving, I have I1 equals I2 plus I3. Or I1 for entering the node is positive, minus I2 because it's leaving the node, minus I3 because it's leaving the node, equals 0. Now for a voltage source, the current is negative, so that when you calculate the power, P equals voltage times current, that negative current will make the power negative, which means the voltage source is applying power to the circuit. That holds true for solar cells too. Let's tie this together into an example for which we already know the answer. A voltage divider. So first I assign the voltage drops, V1 plus minus, V2 plus minus, and that makes sense because these voltage drops have to equal the power supply, and I assume that the current is going in this direction, so I have I1 entering the node and I2 leaving the node. I1 and I2 are equal to each other, and V1 equals I1 times R1, and V2 equals I2 times R2. If I substitute equation 1 into equation 2, I get V1 equals I2 times R1. And then if I solve for I2, I get I2 equals V1 divided by R1. I put 5 into 3, and I get an equation for V2. Then when I use this relationship, the battery equals the sum of these two voltages, and substitute, I get equation 8. And then if I solve for V reference, I essentially get the voltage divider relationship, which is great because that's what we expected to begin with. Now let's twist this example a little bit. What if I, for some reason, assigned I2 in the opposite direction? How would that look? Well, they're both entering the node. So I'd have I1 equals minus I2. V1 is unchanged. V1 equals I1 times R1 because the current is going from positive to negative on that voltage definition. But in equation 3, V2 equals minus I2 R2 because the current is going in the opposite direction of our defined voltage drop. Again, we substitute 1 into 2, and then we solve for I2. And when we substitute finally for equation 5 into 3, the negative signs cancel out. And so ultimately we get the same voltage reference. Now if I solve equation 3 for I2, the minus sign comes back. And all that means is that I chose a wrong direction for I2. Now why would I ever assign the current going across a resistor from negative to positive? Well, you can make a mistake, but in transistor modeling we do this all the time. And in this simplified transistor model, we have a V in, or in this case, it's VG measured to ground. All right, and there's an input resistance, but this is a dependent current source, and it's dependent on VG times a scaling factor, GM. So whatever VG is, this current is VG times GM. That's a simplified transistor. Now, V out of the transistor is measured from V out to ground because that's how we're defining it. V out is a positive voltage to ground, which is the negative. Well, if I substitute V out equals minus the current times RL, and if the current equals GM VG, I can substitute in that. I get minus GM times VG times RL. And then if I want to know the gain, I just divide V out by VG in this equation, and I get minus GM RL. And what this means is that there's a gain in this circuit, but it also inverts the voltage signal. When I was learning this kind of problem, yes, I sometimes really wondered. I thought it was somewhat random the way things were assigned. But if you just keep in mind, you've put a voltage definition down from positive to negative, and you have a current flowing from positive to negative across that device, be it inductor, capacitor, transistor, diode, V equals IR. But if the current is moving from negative to positive to what you define the drop to be, it'll be negative. So if you keep that in mind, you will get the correct answer when you do these circuit analysis problems. And in this transistor model, you will have, it's not a mistake, this current source is forcing the current in this direction. And simple transistor circuits like this do invert the signal.